So, when you think about science, what's the first thing that pops into your head? Probably a lab coat, right? Maybe some bubbling beakers? Or that rigid, step-by-step method you learned in school? Well, today, we're going to go way beyond the textbook. We're diving into the philosophy of science, the deep, fascinating, and yeah, sometimes messy story of how we actually figure things out about the world around us.
I bet you remember this from school, the scientific method. It's always shown as this perfectly clean, four-step recipe for truth. You look at something, you make a guess, you test it, and bam, you get a conclusion. It's simple, it's tidy, and honestly, it sounds great.
But here's the question that really gets to the heart of it all. Is that truly how discovery works? Is the path to knowledge just a straight, easy-to-follow line? As you can probably guess, the real story is so much more interesting.
Okay, so let's start by knocking down one of the biggest myths out there. The idea that science is all about proving things with 100% certainty. I mean, it sounds like that should be the goal, right? But it actually hits a massive philosophical wall.
This idea goes way back to the 18th century philosopher David Hume, and his argument was just devastatingly simple. He basically said that no matter how many times you've seen something happen in the past, you have zero logical guarantee it's going to happen that way again. You know that disclaimer, past performance is no guarantee of future results? Hume figured that out for logic itself.
The classic example that makes this crystal clear is the swan problem. Imagine you're a scientist and you've seen millions of swans, and every single one of them has been white. You might feel pretty confident, but you could never ever logically prove the statement all swans are white. Why not? Because all it takes is just one black swan, like the ones they eventually found in Australia, to completely shatter your universal law.
And this gets us right to the core of what's called the problem of induction. It's this huge puzzle. How can we ever justify making a giant, universal rule based on just a handful of things we've seen? Science has to make this leap all the time to create laws of nature, but from a purely logical view, it's not absolute proof. It's more like a really, really well-educated leap of faith.
So, okay, if science can't actually prove anything is true with absolute certainty, then what makes it any different from, say, astrology or some wild conspiracy theory? This brings us to one of the most powerful ideas in the philosophy of science, all thanks to a thinker named Karl Popper.
This is the exact question Popper obsessed over. If you can never reach total certainty, then what's the point? If you can't confirm a theory beyond all doubt, what separates it from just being a good story someone made up?
And Popper's answer was a total game changer: falsifiability. He argued that the thing that makes a theory scientific isn't that you can prove it's right, but that you can try to prove it's wrong. A real scientific theory has to be risky. It has to stick its neck out and say, hey, if I'm wrong, here's exactly what you would see to prove it.
This is a huge mental flip. Instead of going out and looking for more and more white swans to pat yourself on the back, Popper said a real scientist should be out there actively hunting for that one black swan. The goal isn't just about collecting yeses. It's about trying your hardest to find a no. Progress actually comes from finding out where our ideas break.
So that leads us to the next myth we need to tackle: the idea that science is this slow, steady, predictable march of progress, where we just add one little brick of knowledge at a time. But when the philosopher Thomas Kuhn looked at the actual history of science, he saw something way more dramatic, way more revolutionary.
Kuhn gave us this incredibly useful idea of a paradigm. Now, a paradigm isn't just one theory. Think of it more like the entire operating system for a field of science. It's the whole collection of shared beliefs, the standard ways of doing things, and the unquestioned assumptions that tell scientists what normal work even is.
And Kuhn argued that science moves in this wild cycle. Most of the time, scientists are just doing normal science, basically solving puzzles that fit neatly inside the current paradigm. But then, anomalies start popping up. Weird results that just don't make sense. And as those weird results pile up, the field goes into a crisis. The old rules just aren't working anymore. And that crisis only gets solved through a scientific revolution, where the entire old paradigm gets thrown out for a new one.
In a paradigm shift, a term we get from Kuhn, is a massive deal. I mean, think about the shift from believing the Earth was the center of the universe to understanding it revolves around the sun. That wasn't just adding one new fact to the pile. It was a completely different way of seeing reality itself. It changed the questions, the answers, everything.
Okay, this brings us to our final, and maybe the most challenging, idea we need to unpack. This myth of the perfectly neutral, totally objective scientist who is completely free from any human biases or values.
Look, the truth is, science is a human activity. And because of that, it's soaked in what philosophers call non-epistemic values. We're talking about social priorities, ethical concerns, economic pressures, political wins. All of these things influence everything from what research gets funded in the first place to how scientists interpret their results. It's just an unavoidable part of the whole shebang.
And this influence goes really, really deep. There's this concept called theory-ladenness, which basically means that even the simple act of looking at something isn't neutral. What we see, what we even notice, is often shaped by the theories we already believe. An astronomer looking at a weird pattern of light isn't just seeing dots. They're seeing evidence of a galaxy bending space-time, an observation that only makes sense through the lens of general relativity.
So, if we can't get rid of these values, and we can't, what do? Well, the goal is to manage them with our eyes wide open. That means scientists have to be transparent about their assumptions. It means making sure the values that guide research reflect what society actually cares about. And it means actually talking with the public.
All right, so where does this all leave us? After tearing down all these common myths, have we somehow weakened science? Have we made it seem less impressive? Not a chance. In fact, what we've done is reveal a much richer, more honest, and more human picture of what science really is.
Let's just do a quick recap. The myth: science gives us absolute proof. The reality: it builds incredibly strong evidence. The myth: scientists are trying to prove their ideas right. The reality: the best science tries to prove its own ideas wrong. The myth: progress is a slow and steady line. The reality: it's a series of explosive revolutions. And the myth: science is purely objective. The reality: it's a human process that has to deal with its values. In the end, understanding all this doesn't make science less trustworthy, it makes it more trustworthy. It shows us that science has self-correction built right into its DNA. It's not some rigid ancient dogma. It's a dynamic, humble, and fiercely self-critical process of trying, failing, and learning. It's a powerful human endeavor, not some cold, infallible machine.
And that's really the thought I want to leave you with. The next time you see a big headline about a new study that proves something, you'll be able to ask better questions. You'll wonder if this is just one small finding or part of a really well-tested theory. You'll ask if it's just business-as-usual science or if it's one of those weird anomalies that could trigger a revolution. You'll think about what values might be shaping the research. You'll be thinking like a philosopher of science.